Thank you for your participation and joining us today. We made a strong start to our Quantum Horizons program yesterday, and Ceyhun Hoca delivered an excellent lecture, and we will continue today's exciting lecture. We will continue with Ceyhun Hoca. And okay, it's a pleasure to introduce you, Ceyhun Bulutay, again. So please, Ceyhun Hocam, whenever you like, you can start your exciting lecture today. Thank you.
Thank you, Özgür Hocam and Ali Kram Hocam, and to everyone who joined today. I'll start today with, today is the second part of quantum information, quantum optics part of the prep school. Now, on this issue, quantum optics in Turkey is, I would say, it has some tradition, and it's one of the strong fields in our, physics research, and we owe this to a few people. One important name is Ataç İmamoğlu. Definitely, there is an Ataç İmamoğlu effect in quantum optics, just like the Jeanne effect in France, and maybe Cohen-Tanouji also. So a single figure can really affect the young people, and just kind of like a ferromagnetic alignment. But actually, there is two more names that I should definitely pay tribute in my starting with my lectures on quantum optics and also quantum information for yesterday. So let me now go to my screen share. Okay, so here's my first slide. I hope you see this now. So you see two pictures here. Alexander Shumovsky and Alexander Klyachko, two Russian scientists. They did a big service to Turkey. Alexander Shumovsky is the person who brought quantum optics to Turkey. And he, his PhD students are now very influential scientists, like our chairman, Özgür Müstecaplıoğlu, and Özgür Çakır from İzmir Yüksek Teknoloji Institute, Muhammed Ali Can, and also now they are leading the science in Turkey and internationally as well. Alexander Klyachko, he did, collaborate with Alexander Shumovsky. Both of them happened to be at Bilkent University. They could be somewhere else, but they really served this country. And it just shows us that science is very much international. Alexander Klyachko, his contribution, you may not know him, which would be a pity. He's a mathematician, but he was very well versed in physics, and he made a big contribution, just like the Bell inequalities. The pentagram inequality was developed by him, more or less, together. It was initiated by Alexander Shumovsky, and now people are, the community is realizing how important that contribution was. From Sabancı University, Zafer Hoca has given lots of very interesting talks on the very importance of this pentagram inequality. So they published very influential papers, and they have also brought up new generations of PhDs. So that's how I will start today. Another thing before I start is today I will reserve it to quantum optics. And we have a lined up talk from Barış Çakmak Hoca, which is very important, thermodynamics of quantum control. So I will definitely, cut my, talk, in time. Özgür Hocam, you can just intervene like 5 minutes before I should, wrap up my talk.
All right.
Thank you. Now, quantum optics is a course that I'm teaching as well at Bilkent University. This is a lecture note that belongs to just this semester. This is the class who was very much, successful and just finished this course. So I will upload the lecture notes, some 200 pages, to the Google Drive. Okay, so you will have access to the lecture notes as well as what I talked today. But unlike yesterday, today I will be not writing the equations because they really are quite heavy. So I will, unfortunately, I will go over this written, sheet. I apologize for this. Otherwise, I will not be confined in time, okay, to the allocated time. So what is quantum optics? Now, quantum optics is essentially, it shows the mysteries of quantum mechanics in their bare bones form, without too much mathematical overhead. You get all the surprises, puzzles, interesting things with bare minimums. So it's just like physics is all about interactions. So quantum optics is all about the interaction between light and matter. And most of the time, the quantum aspects come into play, but sometimes it is only the coherence, the classical coherence, which can also give us very interesting, effects. That's about quantum optics, okay? And it's mainly an experimental field. So since the theory is so easy, just you need to be able to, diagonalize, find the eigenvalues and eigenvectors of a 3x3 matrix. That is the level of difficulty of quantum optics. So since the level of, mathematics is so, low, anybody can do the theory, including the experimentalists. So my number one message is quantum optics is by and large an experimental field. Okay, but always you have to test before doing an experiment your models with computations theory. So they are all homemade in a group, okay, in an experimental group. Okay. So having just hopefully conveyed my message, now let me move on to my just, let's say, preview of what goes into this field. First, I'll start with the traditional approach of how do you quantize an electromagnetic wave, okay? Let's start with this. So here's what you see is a cavity, okay? You have two mirrors just bouncing the light back and forth, okay? So I have one mirror here. Where did this come from? Sorry for this. One mirror here, another mirror here, and there is a standing wave in between. Let's say this is its wave vector. It has this many, oscillations. We are just considering a fixed mode of this cavity, okay? So electric field must vanish at the boundaries. So this is the mode profile, and it will oscillate in time, okay? So this thing is the time amplitude of electric field, okay? I'm using SI units here. And there is the associated magnetic field. So because of Maxwell's equations, there is this simple relation between this amplitude and the amplitude of the magnetic field. So this is just easy electromagnetism. And you can calculate the stored energy in this cavity, in this box. It's the electric field's energy density, magnetic field's energy density integrated all over the cavity, all over the box. When you do this, you get the amplitude squared of the magnetic field, amplitude squared of the electric field. That is the stored energy, and it oscillates, okay, with the total energy being constant, obviously. If there is some high magnetic field, then there is a decrease in the electric field. It's an oscillation. Now, so far everything is classical mechanics. Now, what you do is you say, look, the position, like quantity, this amplitude of the electric field and amplitude of the magnetic field, if we make them operators, not C numbers, which respect this operator non-commutation, just like position and momentum, then this energy expression turns into a simple harmonic oscillator. Okay, just a trap and a mass in a quadratic trap oscillating back and forth. It is just isomorphic to a simple harmonic oscillator. That's very interesting that all oscillators, like an electromagnetic, a field oscillation or a mechanical oscillation, they are all the same, or an LC circuit, they are all the same. Okay, so it's not a surprise. But now, through this gate, we now move on to a quantum mechanics by making these become operators. There is a much neater way of obtaining this through Lagrangian densities. You can just take a look at this in the lecture notes or any quantum field theory book. Nevertheless, we know how to deal with, hopefully, harmonic oscillators. We introduced these lowering and raising operators. So in terms of those operators, you can write the electric field is now an operator, which involves lowering and raising operators. This is the mode profile. Okay, same thing for the magnetic field. It is now an operator, and these two things do not commute, they are operators. So you cannot simultaneously measure at the same spot electric field and magnetic field, for instance, which is coming from the quantum mechanics, this commutation. Okay, then you are good to go. The rest is just downhill. If you use for this commutator this definition of raising and lowering, you see that these mode operators they satisfy much simpler commutation relation. So then it is just the harmonic oscillator ladder. There is a ground state, end of the road. You act with lowering, and you come to the ground state. And if you want to go up, you excite one more quantum with raising operator. So this is how you traverse this energy ladder. Okay, for normalization purposes, there must be the ground state. Okay, the ground state is defined by no more lowering allowed. You hit to the vector space 0. Okay, now here comes my first homework assignment. If anybody is interested, what you will do is you will just insert the definition of the electric field and find the expectation value of the electric field for any number state, let's say number 3 or any generic number n. You will find out that it is 0. So these number states, they have a very interesting feature. The mean electric field on those number states, they are 0. But they have fluctuation. The square is non-zero. It is just something like this. Okay. So we now start getting some quantum weirdness. Let me just show you, which is not so much critical, how you would generalize this to multi-mode case. In a cavity, you have all other cavity modes as well, like fundamental mode, first excited, whatever, I wouldn't say first excited, so higher frequency mode, let's say. Okay, so in that case, you just do this repeatedly and independently. They do not talk to each other. So for each mode, what you see is a ladder of states at some energy omega 1 or another energy omega 2. So you have decoupled oscillators for each mode. And they don't talk to each other unless you put some material that will link these modes together, nonlinear optics, which is not the case so far in our discussion. Okay, so it's not a big deal to move on to multi-mode case. So I go back to single mode case, only one trap, and we introduce some dimensionless quantities, x1 and x2. Essentially, they are the electric field and magnetic field operators, but throwing out the coefficients. So these are the so-called quadrature operators, which are electric field and magnetic fields. But they are simpler because of those unnecessary SI coefficients. So these two operators, quadrature operators, they satisfy a nice commutation relation. So just like electric and magnetic field, they are not simultaneously measurable. And they satisfy this Heisenberg uncertainty relation. Now, for the number state, okay, a number state where you are, let's say, at the third ladder or second ladder, these are all number states, definite number of photons here. So this one has 3 photons in your cavity. This one has 2 photons in your cavity. This one has 1, and there is the ground state. No, it's the vacuum state. So for all those cases, if you just take a look at the mean values, they vanish, just like electric field and magnetic field vanishes for definite photon number state. Okay, but the fluctuation is large, and the fluctuation grows with the number of photons. So this is the first quantum photonic state that we now encounter. We see an object like this, which contains n photons, but there is a lot of uncertainty when you have that many photons with definite photon number. Electric field and magnetic field, they are very much uncertain. Okay, or another way to look at these definite photon number states or Fock states, they are also called Fock states, is that you are so precise, you are exact about number of photons. It is whatever this number is, but you are totally imprecise or uncertain about the phase. It is all over the place. Okay, it's just a 2 pi. It can be anywhere on that 2 pi span. Okay. There is another photonic state which you know already. Özgür Hocam, is there something?
Yes, I have a question. So, according to your expressions, zero state has some energy, no?
Yes.
Yeah, maybe this is also something we should also discuss with Professor Sergienko, because yesterday his argument was the zero state carry no energy, and it can be used for gas state measurements for single particle entangled state.
Özgür Hocam, you are very right. I will come to that because I am also puzzled with Alex Sergienko's comment. So I'll come to that, definitely. Okay. So I'm glad that you brought that question up yesterday. So I'll come back to that and we can talk.
Yeah, it piqued my curiosity, and I am so persistent till I understand it.
yeah. I mean, yeah,
okay.
I'm also confused. I'm definitely confused about his comment. So just to clarify these, even the vacuum state has the 0 point energy, h bar omega over 2, whatever your frequency is. So all of these have some energy. all these states. But maybe Professor Sergienko is discarding vacuum energy. Well, I'll come to that. Let me introduce something simple, laser light. Laser light is a very close approximation, something called coherent state. Coherent state is a mathematical construction. These so-called lowering operators, they have an eigenket. They do not have an eigenbra, but they have an eigenket, which satisfies this eigenvalue equation, where alpha is a complex number. So this simple entity defines something called coherent state. It is so coherent that I'll not mention more about higher order coherences, but it has an infinite order of coherence. In this new construction, which you can express a coherent state in terms of number states of infinite summation. Okay, this is a complete basis. So with number state basis, you can express anything like coherent states. Okay, but the interesting thing about coherent states, now electric field expectation is non-zero. It's a sinusoid, just a sinusoid. Fluctuation is something like this. And standard deviation is just this much. It is bounded. It is not growing with number of photons. Okay. Another homework that I will ask you is to verify these three results. But what a coherent state is it's not so classical, but it is the most classical light you can get in quantum mechanics. It is a very bounded uncertainty, but it has some expectation value sense. It is just like classical radiation. Okay, so there is an uncertainty, and this on the quadrature space, this thing is just traversing a loop at the frequency of your electromagnetic waves oscillation. Okay. Here comes the next thing for quantum optics, very crucial, squeezing the uncertainties. Okay, so this is now a result that just tells us if two operators do not commute, then they should obey. It follows from triangle inequality, Schwarz inequality, that they should obey this relation, Heisenberg uncertainty relation. It's a product. So you can squeeze the uncertainty in one quadrature or in one operator at the expense of the other. That's the squeezing. So if you want to control things, but you will not beat Heisenberg uncertainty relation, this is always respected. But you can take the liberty to squeeze the uncertainty in one quadrature below that of the coherent state's minimum uncertainty value. So this zone here is where X1 quadrature has less uncertainty. Okay, and this is the opposite squeezing. So the uncertainty, let me just show you on the vacuum state. This is the vacuum state. I'll have a drawing on this. So this is the X1, X2 quadrature. You can actually make this thing narrower on X1 at the expense of X2. Now X2 is, fatter, but it is, thinner on X1. So that's squeezing. And there is a mathematical construction that does the squeezing. It is this guy. This is the operator. When it acts on a coherent state, it squeezes it by this amount. So this is the squeezing parameter, which has some squeezing, extent and orientation on the phase space. Okay. Now this looks horrible, really. Exponential sum quadrature terms. I'll come to that. but actually it requires a two-photon process and nonlinear optics. There is some tool in quantum mechanics. Everybody in this game knows this very well. Baker, it is called, Baker-Campbell-Hausdorff lemma. You can derive that those squeeze states, they have these funny expressions. So if you squeeze on one quadrature, let's say, you are exponentially squeezing one quadrature and exponentially anti-squeezing the other quadrature. So you can play these games and squeeze uncertainties without beating Heisenberg limit. That is, to our knowledge, unbeatable. Now, how would you get such a squeezing? Well, what you need to get is just the exponent. You just need to generate this. And to generate this, it's a quadratic process. So it's a nonlinear optics. Professor Alex Sargienko mentioned this spontaneous parametric down conversion. There's a crystal, you can pipeline or whatever, you can have periodic pollings, whatever. And in any case, you send a high energy photon and two half frequency photons come out and in the degenerate case. So in the degenerate case, this is the Hamiltonian. So these two things, signal and idler, they are the same operator. So this is the exponent that you aim for in the squeezing. In the squeezing's exponent, you need this. And when you evolve the Hamiltonian, it jumps to the exponent. So it generates this thing in the exponent. So it generates squeezing. Okay, so you just wait. That's all you do. You wait for this coherent light to pass through the crystal. And in that duration, it will become squeezed. If you wait too much, it will become anti-squeezed. So it will repeatedly go through these cycles. So you should know, pre-calculate when you should take it out of the medium with the desired squeezing. And what comes with squeezing is entanglement. So these two pairs, idler and signal photons, they are also entangled. And that was what Alex Sargienko was referring to in application. Okay, those, it was a very influential work that they have done in 1997. Having said this, I will just mention a few other non-classical photonic states. One of them is a cat state, Schrödinger cat state. Why is it called cat? Because a coherent state is a laser light. It's a kind of a macroscopic photonic state. If you just take two coherent states and superpose them, which is difficult, extremely difficult, you get an interference in between as well. So this is something called Wigner plot, just a probability distribution plot. And there are Wigner negativities that shows the quantumness of this photonic state. I'm just throwing out words to you, make you aware of such terminology. So what you are doing is a superposition of like spin up and spin down. This is coherent state at alpha and coherent state at minus alpha. If you can keep this superposition, then this is very powerful. This is called an even cat. This is called an odd cat. So the phase in between makes a difference. And you can even superpose two of these into a four. Okay, higher superposition, even more difficult. Okay. And these are so fragile, these superpositions, they very quickly decay into mixed states, a mixture of this and mixture of this, statistical mixtures. Okay, so environment does this. Now there's another interesting state, noon state. It is two modes, A and B. In one mode, you have n photons. In the other mode, you have 0 photons, and vice versa. This is called mode entanglement, and that is what actually Sergienko was, he had a mistrust on this. Okay. Now, the interesting thing is null states, they are well-established photonic states, and especially for quantum metrology, people are, very much advocating those null states. Now, these null states, they are generated by beam splitters. So I will just mention something very, in the, alphabet of quantum optics, there is this important effect, Hongo-Mandel effect. It was relatively recently discovered, like 60 years after quantum mechanics was discovered, but it's so simple. You take a beam splitter, 50-50 beam splitter, okay, and you send one photon from here, one photon from here. If these two photons, if they are truly identical, in that case, even though there's 50% of coming out from port C and port T, quantum mechanics just gives you this result. They will either come, both of them from this port, or both of them from this port. It's a null state of n equal to 2. Okay, so null states they are not difficult to generate, just a beam splitter. But I guess the issue is this entanglement is something that can be harnessed or not? I think that's the mistrust that Professor Sergienko has. But in any case, this is Hongo-Mandel effect is very important because this is just an explanation why this occurs. There's a cancellation if these are truly inexclusive photons between these two paths. Double transmission and double reflection, they cancel. This has a use. The Hongo-Mandel coincidence count has a use in quantum optics. There is so-called you have single photon sources that are fed to the beam splitter from either end, and you have a freedom of playing with the delay on this end. So you are sweeping with the delay so that you want to guarantee that these photons, they will arrive to the beam splitter at the same instant. So when they do, in that case, you expect that either both of them will go here or both of them will go here. So there will be suddenly a dip in the coincidence, okay? Double click here, no click here, so 0 coincidence. So there's a dip, so-called home dip. And this is a good check of indistinguishability. So generating indistinguishable photons is a big business in quantum technologies. You must, persuade people that your photon sources are truly indistinguishable, and the check is simply a beam splitter 50-50 and coincidence counter. This is kind of electronics. That's all. So in the remaining few 10 minutes, I will move on to the rest of quantum optics, which is now including matter and light. Because actually, like in squeezing, you need matter to actually generate those photonic states. So light-matter interaction is at the very heart of generating those photonic states. So there comes the main part, the interaction part of the quantum optics field. And there are a number of model Hamiltonians that one should just study, and then again you are good to go. First one is the Rabi model. This is very old, 1930s, 35 or whatever. That was the the birth of NMR. So NMR is actually the father of quantum optics. Okay, just the spins and spin echoes, all those, they were generated now like 40 years before, or maybe 30 years before laser. So all of the knowledge of quantum optics was already there before we had laser and coherent light. This is just based on spins and with radio signals, how you play with spin polarizations. Okay. Now it's the first one, the Rabi model is semi-classical in the sense it's the coupling between an atom, a two-level atom. Let's say this is the ground state of the atom, this is the excited state of the atom, with classical light. So light is just a classical electromagnetic field. It's not quantized, but atom is discretized, so it is semi-classical. So here what you have is a radiation which has an energy h bar omega. Let's say if that energy doesn't make it for the full transition energy, which is h bar omega 0. So there is a detuning in general. Now this detuning is the most important control parameter in quantum optics. Is it on resonance? Is it red detuned, blue detuned? This is the only thing you have, but this is actually the most important control now. So what can you do with Rabi model? You have an incoming very coherent electromagnetic wave, so you can derive coherent oscillations of the electron in this two-level system. So depending on your detuning, you can have either, if it is on resonant, you can just start from the ground state and put your electron to the excited state. If you wait too much, it comes back to the ground state and it oscillates like the black line here. If you have some detuning, then the probability of excitation is not up until 100%, but it is less. We can still have a probability of excitation without conserving energy, okay, with detuned laser. There's a graphical illustration of this. The density operator of the atomic system can be expressed, the entries, this 2x2 matrix entries, they can be expressed as some XYZ Cartesian components of a vector. It just tells how this arrow moves under some incoming light, depending on the detuning of the light and how strongly it is coupled to the two-level system. Okay. So you can just play by the detuning and the Rabi frequency, so-called. You can just make this polarization rotate as you like. You can play things like photon echo. This is something in Ramsey interferometer. Cengiz Hoca yesterday mentioned without this guy in between. Actually, the things that were developed for nuclear magnetic resonance, all those tricks and in your toolbox, they work extremely well in quantum optics. So the Rabi model is one of the most important iconic models in quantum optics and NMR, because that tells you how you control coherence in the matter system. You can go beyond Rabi model and include quantized electromagnetic field. Now, see this. This is our electric field operator. So if you also quantize the electric field, that makes it quantum Rabi model. Amazingly, only 11 years ago, this Hamiltonian was exactly or analytically solved. It took so many years, or maybe people didn't fight enough. But that was the surprise. Like 10 years ago, a young scientist from Germany, Brack, he just showed that this is analytically solvable, and that really gave a big motivation and insight into superconducting qubits. Because that is where actually this quantum Rabi model and strong coupling, ultra strong coupling, whatever, all those things in superconducting qubits, superconducting, let me write qubit here, transbone qubits, whatever, this quantum Rabi model is very interesting to have. Okay, so it's the Rabi model with quantized electromagnetic field. What people already had before Brack, quantum Rabi model, was an approximation, throwing out something called rotating wave approximation, some terms which gave rise to some simplification. So this is also analytically solvable, Jaynes-Cummings model. And Jaynes-Cummings model gives you interesting quantum effects, Cummings collapse, Cummings revival. We go to so-called rest states, Alpert-Towns effect, Mallows triplet. So even with just 2 levels, but with strong electromagnetic driving with quantum light, you can generate lots of quantum surprises. You can go from 2 levels to multi-levels. The Dickey model is another Hamiltonian, which gives rise to something called super radiance. Okay, so you can just have a bunch of 2 levels, let's say two levels, but even though their spontaneous decay is independent, if they decay into the same electromagnetic mode, then they become correlated and they decay much faster with super radiant light. Okay, so super radiance is something interesting. What is even more interesting is subradiance, avoiding radiation, slow radiation. This was experimentally more difficult to achieve subradiance. You want your system to be kind of immune to radiation without playing with the cavity, those effects like rejection of that cavity mode and such. Another thing that you can play with quantum optics is 3-level quantum optics. So in these 3 levels of atomic states, you can just make different configurations, ladder, V, lambda, and you get different effects: electromagnetically induced transparency, stirrup, lasing without inversion, coin population oscillation. So all of these are technologically so important. Electromagnetically induced transparency allows you to slow down electromagnetic light, even stop light. So these are technologically very important. People were kind of contemplating on photonic memories with EIT. Something I'm very proud of. Özgür Hoca and Özgür Hoca, Özgür Oktel and Özgür Müstecaplıoğlu Hoca, they also have electromagnetically induced left-handedness. It was a big achievement when actually they published this. They were just assistant professors at that time. So my final slide example is this, optomechanics. In optomechanics, the matter side is a mechanical system. So you have a cavity, and one mirror is mobile. Okay, the other end mirror is fixed. So with radiation pressure in this, you are also pumping this from outside with huge lasers. And this radiation pressure is kind of trying to move this one mobile mirror, and it is attached to some mechanical system, which, let's say, here like a spring. So you are coupling mechanical vibrations to photons radiation pressure. This is the Hamiltonian that describes this. This is the energy of the photons. These are the energy of the mechanical vibrations. And this is radiation coupling between number of photons in your cavity and the displacement of the mirror. Okay, so why would anyone do this, right? So as you know, the most popular example in optomechanics is LIGO. Okay, in LIGO, gravitational wave detection, you really shoot for avoiding mirror displacements, to the level of 10 to the power minus 20 meters or so. Okay, so you must definitely cool down the vibration of your mechanical system to its ultimate ground state level. So this you can achieve cooling the mechanical system, or you can also cool the light, the photonic system as well. It depends on what you like. So this optomechanical coupling allow you to control one system at the expense of the other. So you can entangle photons and phonons. This allows for entanglement generation if you are in the blue detuned regime. You can squeeze either the mechanical modes, or you can squeeze the cavity photonic modes. You can generate, just like EIT, optomechanically induced transparency. You can induce these transparency to a probe light by mechanical induction. You can generate photon blockade. And now recently there is a very important field of non-Hermitian PT symmetric systems. So optomechanics is growing. Experiments are growing. Lots of groups are joining to this field, and it's a growing field. So that's all I wanted to say about like just a quick tour of quantum optics. Okay.
Thank you so much, Ceyhun Hocam. It was a very nice talk and very nice overview at the end. We do have one or maybe two questions in the chat. Would you like to read them on your own, or?
Okay, yes, let me see.
Okay.
So Bura, I saw an expression in the previous page. That previous page is very previous, let's say, saying that even odd cat states have super sub-Poissonian distribution. Bura, you are a very quick reader, very good. I'm confused with this. Can you explain it in a sentence? Because one classical and the other is quantum mechanical photon statistics. I don't know how even and odd cat states have an impact on photon statistics. Actually, the coherent state as is has the Poissonian distribution, okay? But you can play with the statistics by coherence. So these cat states, you can engineer their statistics. You're right in saying that coherent state is like classical. In a sense, it is. But then you are really in those cat states, you are generating a very quantum object. There are so-called Wigner negativities. So unlike a single coherent state, a cat state is more quantum in a sense. It's too much, different than a single coherent state, which is Poissonian statistics. So that's my motivation. It's really preserving that superposition is everything, and that brings in a new statistics. Again, on this, like Özgür Hoca can comment if he likes, because he's very much experienced on any branch in quantum optics. Shall I move on to the next question, Özgür Hocam?
Yes, please. I do have some comments, but I don't want to extend the discussion. I think your answer should be sufficient. If anybody wants to continue discussions, they can ask more questions. But Cengiz has some 3 questions, so let's proceed to them.
Okay, so in the harmonic oscillator description, in the very beginning, you mentioned that E and B operators which do not commute. If E and B operators do not commute, how does Maxwell's equations connect them? What did I miss in your reasoning? Well, I mean, there can be, like position and momentum. They do not commute, but there is an overarching dynamics that governs, Schrödinger equation. So there can be, and this is always the case, right, Cengiz Hocam? There is an overall dynamics which is, governing those dynamical variables which do not commute, just like in mechanics, in quantum mechanics. So this happens in quantum mechanics as well. So this puzzle, even though position and momentum, they do not commute, there is an overall Schrödinger equation, or just the quantized Newton's law, let's say, which governs the both 2 non-commuting entities. So I think this is, to me, it's not puzzling. Okay. So it just limits, their non-commutation just limits, the precision. Maybe I'll go to the second one. All of these are deep questions. I'm sure there can be much better explanations than what I'm giving here. The second question from Cengiz Hoca, you mentioned the precision trade-off between photon counts and the phase. Okay, how do you precise single photon detection measurements of photon counts and how do we do precise single photon detection measurements of photon counts and jitter? I'm sure you are a better expert on this thing than I am. So I may say something about this, but I'm kind of hesitating because I'm sure what I say would be already apparent to you. So, the photon detectors, they just respond to the photon number. So there is absolutely no information about the phase of the photon. Here I don't see some contradiction. I'm sure I'm missing your point here, Cengiz Hocam. How do you prepare squeeze states? Okay, so there are many ways of preparing them. As I said, you need at least a quadratic interaction that will generate some, like nonlinear optics, so that will generate squeezing. Okay, so with interactions, and those interactions that they being quadratic may be kind of disguised, like in optomechanics, it is not so apparent, but if you just do something called adiabatic elimination in optomechanical Hamiltonian, then you realize that actually through the mechanical link, there is a quadratic interaction, back action, okay? So in any case, it may be disguised or it may be apparent, but you need a nonlinear as a square term of your excitation, the A or A dagger, and it must be Hermitian. So if you have A dagger squared, you must have A squared as well. That's how it is. Shall I move on to the next question? Özgür Hocam, do we have time?
Let's take one more question, then we will proceed to our next speaker, Barış.
So Muratan Alpay, can we think of as duals the variance and zero mean value, like the average value and RMS value of a sinusoidal? I guess it is, although it is the classical circuit theory. What can be the similarities? RMS value, indeed. Yeah, indeed, the standard deviation is the RMS value. It is the root mean square value. There is nothing quantum there. So what you know already from good old statistics, circuit theory holds here. So you're right. It's the RMS value is the standard deviation.
Thank you again, Ceyhun Hocam. And thank you for all the questions. Now we are perfectly on time to move on to our next speaker.